Okay, so we talked about binary trees in the last unit, and now I want to talk about arbitrary trees. So what do these look like? Well, remember a binary tree, every node could have one, the internal node could have one or two children, right? If it had no children, then it was a leaf. For arbitrary trees, we also have a root, but what we want to have is not just one or two, but as many children as we want. Okay, and each child can have a bunch of children, right? And so they're really much more general trees. Other than that, the shape still looks the same, right? We still have a root, we still have internal nodes, we still have leaves, and the tree is always pointing, kind of going down from the root to the leaves, right? All of that stays the same. The only thing that we're moving away is the restriction that there have to be at most two children. So here's how we can do that mathematically. When I think of a tree, I'm now going to have a payload, right, or an element, okay? This is what I would be inserting into a tree. And now I need to have as many subtrees as I want. So it can't just be a left and a right subtree. I have like T1, T2, T3, up to T sub n, right? And the easiest way to kind of capture that is just to simply have a list of trees, right? And so that's how we define a general tree. It's actually a list that has an element and is followed by a list of trees. That's our recursive or inductive definition. Okay, so let's try to do that in ACL2, and here we have it. This is the def data command, but I want you to contrast this with some of the def data commands we've seen before, like for example for binary tree. Okay, what we would have there is that a binary tree is one of, right, nil, right, or it could be a list of an integer, say, and then a binary tree, and then another binary tree. Okay. Here we actually have to do a little bit more work, and the reason for that is that I need to define not just one type, which is tree, but to define two types at the same time, because a tree contains a list of trees, right? So what I need to do is define two types. Here's type number one, and that is a tree that is a list, right? It's a pair of an integer and a list of trees. Okay, and now I need to define what a list of tree is. This is kind of part two. And a list of trees just, well, actually we use the list of primitive in def data to just say is a list that contains 0 or more trees. Okay, but see, I can't talk about a list of tree unless I talk about trees, so there's kind of a dependency going this way. And I can't talk about a tree unless I talk about a list of trees, so there's a dependency going that way as well. So that's why I need kind of a mutually inductive definition. And that's why the syntax is a little bit different. In particular, right, I want to draw attention to these parentheses here, okay, as if we needed more parentheses, right? But the reason those parentheses are there is because I'm actually defining more than one type. In here, there is no parentheses there. That's because I'm only defining one type, so I can get away with a simpler definition. Okay. So we know what a tree is. I want to just kind of take a little side note because for general trees, I've decided to show you this kind of in a different way that I did for binary trees, right? And you can decide which one you like better. I think they're both actually correct. Okay, and that is that a tree, okay, has to look like a list, right? That contains an element and then a list of trees. That's the way it always looks like. In particular, a tree cannot be nil. Okay, so one of the things that means is that there is no empty general tree, the way that we had an empty binary tree. Okay, and the reason for that really is that when we're talking about binary tree, a binary tree had a left binary tree and a right binary tree, and so we needed to allow that to be empty, right? I could have defined it so that it had either nil or a left tree and either nil or a right tree, but that seemed more complicated. So that seemed like a natural way of defining it, and we paid for that. Because when we're doing the theorems, we have to keep saying, oh, except for the empty tree, right? So this is a different way of doing it. We're not going to have empty trees. So in that sense, it's actually simpler than what we did before. Okay, so there is no nil tree. We're not going to have to keep adding that in the theorems, right? Except for the empty tree, right? So in that sense, it's simpler. Okay, which definition is correct? You know, I don't think either one of them is really. So I want to bring this idea to your attention. Let's say we're running code in C++, then it would be natural to have something like this: tree star tree, and that's equal to the null pointer, right? Or 0, if you will. Okay, but notice that this is a pointer to a tree. Okay, so I have a pointer to a tree. It's okay to make that null, right? I mean, that's just a pointer. Okay, so that would be okay. In Java, the code actually looks like this. Okay, now here I don't have a pointer, I have an actual tree. Okay, so if you take the C++ perspective, it looks like a tree. I can actually force it not to ever be empty because I can have a null pointer instead of an empty tree. In Java, I don't know, you know, I feel a little bit queasy. So again, that's just my way of showing you that these are questions that are not easily resolved, and they're done by convention. You know, somebody just says, okay, let's go this way, and that's the way we go. Okay, so let's try it this way and see what that gets us. Okay, so let's try by defining some of the functions that we did before. So here is the size of a tree, right? And remember that this is a number of nodes, right? Okay, and the way that we're going to define it is following the same structure of the inductive definition of the type. Okay, so definitions follow the structure of the type. And I talked about that earlier, right? But maybe it wasn't as immediately clear because we were working with fairly simple types that had very little structure. Okay, so if I'm going to process a list, of course I process the first element and then the remaining elements of the list. That follows the inductive definition of list type. But now what I'm going to do is my inductive definition of tree was actually mutually recursive. Guess what? I'm going to need mutually recursive functions. Okay, and the way they're going to work is one of them works on a tree, right, which means an element in a list of trees, and the other one just works in the list of trees. So here we have an example of that. The tree size of a tree, it is simply 1 plus the size, okay, of all of the trees in its list, right? We have to add all those up. So here's what the size of a list of trees is. Well, clearly it's 0 if the trees is nil, right? Remember, this is a list, so it would be better to write it like this. If trees is the empty list, then yeah, of course the size is 0. There's nothing in there. Okay. Otherwise, well, it's just like adding up all the elements of a list. We take the first element, right? So this is just the first tree, and this is the remaining trees. Right? So that seems like a perfectly good definition of what is the size of all of the trees in this list, okay? And that's exactly what we need. If I know how many nodes there are in my children, just add 1 to that, right? And I know how many nodes there are in the entire tree. Notice there is no case for the empty tree because there is no empty tree. Okay, so how about the number of leaves, right? Excuse me. That one's actually slightly tricky. And again, we're going to need the number of leaves in a list, right? And that's defined as before, which means if the trees, which is the list, is the empty list, then yeah, it's 0. Otherwise, first element of the list and then the remaining elements of the list. Okay, but this one is actually slightly tricky. And here's what I want to think about. I have a tree, right? And I kind of have 2 possibilities. I always have the node itself, right? And it could just be that, right? I mean, this could be all there is. Or it could look like this, where there's the root, and then there's a bunch of children, right? Well, this is case 1. If it looks like that, then the number of leaves is actually 1, right? Otherwise, this is case 2, right? And in case 2, the number of leaves is just the number of leaves in my children, okay? Because the node itself is not a leaf, right? So we actually need to have a case split here. Is the root node a leaf? Yes. Okay, then the answer is 1. Otherwise, it's just however many leaves my children have, right? So this is kind of interesting because that's a case split that's not based on the inductive definition. It's just a base case that happens because the root could be a leaf, right? And so we have to be careful. Okay, about the height of a tree, we're going to make the same kind of split, okay? Because if I have a tree that looks like this, right, and there's no children, then the height of that needs to be 0. So this is case 1, okay? And if it actually does have children, right, then what I want to do is find the maximum height of the children, right? And then add 1 because of those extra edges, okay? So yeah, that looks like this. The height of a tree is 0 in case 1, which means it's just a leaf. Otherwise, it's 1 plus the height of the list of trees, right? How do I find the height of a list of trees? If I'm talking about the empty list, then it's just 0, right? Otherwise, I find the maximum of the first, right, versus the remaining. And that will give me the largest height of any of the children, right, which is going to be the correct answer. Okay, so that's pretty straightforward, right? We just replaced plus with maximum, basically. Another definition that we had was this notion of a full tree, right? So our idea of full tree was that all internal nodes have 2 children. But what do we want now, right? Shoot. Okay, so we have to reconsider because we don't have a notion of what the maximum size should be. But let's make that happen. Okay, so instead of saying I'm going to force trees to have a maximum of say 4 children, I'm just going to say they have some maximum. Okay, and so for an n-ary tree, I want all the internal nodes to have n children. That would seem that it works, right? For a tertiary tree, all the nodes you have 3 children. So yeah, maybe that's the ticket. Okay. It kind of does, okay, and we could run with that and continue the proofs, but I don't want to, okay. And the reason I don't want to is because I'm aware of some data structures that have some really nice properties, okay. So for example, there's something called a 2-3 tree, right? And a 2-3 tree is a kind of balanced tree, okay. It's actually a very nice data structure, and the property that it has is that the children, always split either into 2 or 3 children, okay. So it could be 2, but it could also be 3, right? So this is like a tree that's maybe has a little bigger, right? A little wider than a binary tree, but not as wide as a ternary tree, right? It's in between a binary and a ternary tree, okay? So how many leaves can we have? Well, if it always does binary, right, then it's going to be 2 to the h. If it always does ternary, then it's going to be 3 to the h. So I expect the answer to be in between 2 to the h and 3 to the h. Okay, that seems useful. And like I said, this is actually a very useful data structure. Okay, it's almost certainly one that you'll cover in the algorithms course. So as opposed to just saying I have an n-ary tree, so I need all of the nodes to have internal nodes to have exactly n children, what we're going to do is just find what the minimum and maximum order of a tree is, right? And the order, right? Order just means number of children of any node, okay? So what we want is to say, okay, a 2-3 tree, the min order is 2, the max order is 3. Let's keep it that way, okay? And let's see what that does to our protocol, right? So how do I find the maximum order of a tree? Well, let's look at a root, okay? So it looks like this. Let's say that I have 4 children, and of course those are going to be subtrees, right? So the max order is at least 4, right? And then I got to ask each one of these, what is your max order, and then pick the maximum, right, of the max order here and the 4, okay? So that's what this does, okay? So we find here, basically this is the max, this is the order, right, of the root. And then this is going to be the max order of the children. Okay? And whichever is the maximum of those 2, well, that's the maximum order of my tree, right? Now, what about a bunch of lists, right? Then it's going to be similar to some of the code we've done so far, except we're using max instead of plus. So if it's an empty list, right, then the answer is 0, right? You know, there's no children to have any splits, so I can't really pick it, okay? Otherwise, what I'm going to do is look at the first child, right? So this is the first tree, and then look at the remaining trees. And whichever one of those two is bigger, that's the max order, right? So I just take max, okay? I do point out here that leaves are just simply nodes that don't have any children, right? So what's the max order of a leaf? You know what? That's just going to be 0, right? Because I'm going to take the length of the second tree, which is the number of children, that's 0, and then the max order of the children, well, that's 0, so the maximum is actually just 0. That works really nicely, okay? Things don't always work out that well. Always check, right? It's kind of nice that we don't have to explicitly test for that. Okay, okay. Now that's max order. Of course, we should have min order, right? And so here's the equivalent definition for min. All I did was I changed the word max to min and decided to run with that. And unfortunately, that doesn't work. Okay, so here's why it doesn't work. Let's suppose that I have a tree that looks like this. Okay, just a simple tree. It's actually a binary tree, right? So this guy would say, oh, is the max of 2, right? That's the number of children, right? And then the max of my 2 children, right? Okay. Now here it will say, oh, that's the max of 0 because that's the length of the children. I'm sorry, the minimum. Minimum of 0 because that's the length of the children, and the minimum of the height of each one of those. So that's just going to return 0. This is going to return 0. Okay. So this becomes the min. Okay. The min of 2 and 0. And that value, of course, is 0. Okay. So with max, whenever we saw something that was not a leaf, right, then we actually had a non-zero max order, right, because it was at least as big as the number of children. So we always had kind of a non-zero max order. And okay, so the leaves were sending 0 up from the bottom, but because we're taking max, we would always pick anything that wasn't a leaf, right? But now that we're taking the min, it doesn't work that way, right? It seems like it should, right? Is the minimum order of each one of my leaves, I'm sorry, each one of my children, surely that has to be true. But the problem is when one of them sends up 0, then we go, oh, then it's 0, right? So what we need to do is take care of that 0 a little bit more carefully, okay? So here's the definition that actually works. And the way to make it work is actually just to define this new function min plus, okay? So min plus of 0 and y is just going to be equal to y, okay? Likewise, min plus of x and 0 is just going to be equal to x, right? And min plus of anything else is actually the minimum of those things, right? And this is x not equal to 0 and y not equal to 0, okay? That's the only way that you can use that third rule there, okay? So that actually takes care of it, okay? So it really is the minimum number of the minimum fan out, and don't get confused by the leaves, right? Just avoid the leaves at all cost. So that's the minimal change that actually makes that code work. So that's what we're gonna go with. Okay. So now let's try to build, some of the easy theorems. Like I want the one that says that if we have a maximal order, max order of capital M, okay, and height h, right, then we have at most m to the h leaves, right? So for a binary tree, this would be at most 2 to the h leaves, right? Yeah, I think we can prove this, right? So we're going to use structural induction, okay? And if it's a leaf, then h is 0, right? So 1, which is the number of leaves, is less than or equal to m to the 0, which is 1, okay? I have to be a little careful here. M to the 0, right? M is actually equal to 0 in this case, right? That's the max order because all I have is a leaf. So 0 to the 0, you can argue that that's equal to 1. Anything to the 0 is equal to 1. You can argue that it's equal to 0. 0 to the anything is equal to 0, okay? So that's one of those. Just like the case I've been talking about with trees. Is the empty tree a tree or not, right? So yeah, that's arguable, right? Mathematicians have come to the conclusion that the most convenient answer is 0 to the 0 is equal to 1, okay? So I'm actually using that fact, right? I'm just letting you know because it looks like it's obvious, right? But only because you don't see the 0 in DM, okay? So otherwise, right? So this is kind of the this is the induction step, okay? So the theorem holds for all of the children of t, right? The height of each child is at most t minus 1, so here's what we have. NL of t is less than or equal to NL of t1 plus NL of t2 plus NL of t3, all the way out to however many children the tree has. Well, it can't be any more than capital M. Right? It can't be any more than that because that's the max order of the tree. So what we'll do is we'll just assume the worst, right? That is actually equal to capital M, and that's how we get this, right? This is actually the induction hypothesis right here, okay? Because what I'm saying is NL of Tm or NL of Ti can't be any bigger than that, right? That's the less than or equal to. And there can't be any more than M. That is because, as you say, this is the induction hypothesis, and that capital M there is the max order. Okay, and of course m times m to the h minus 1, that's just m to the h. So that's the inductive case, right? The base case works, the inductive case works. We're in perfect shape. Okay, so yeah, that was a pretty easy proof in the case of binary, and it's still pretty easy, so I'm happy. Okay, so now let's try to find kind of the lower bound. And so we did this, right? We found that the size of the tree was less than or equal to 2 times the size of the leaves, the number of leaves, right, minus 1. Okay, yeah, we did that. And now how do I generalize that? It might seem obvious that perhaps the generalization is, I need a lower bound, so maybe it should be, instead of 2, that should be the min order times NL of t, right? Except I wouldn't feel comfortable with that, right? Because if I have a binary tree, I don't know if it's full. Yeah, so that's actually kind of a difficult thing to decide. Okay, so let's draw some trees to find that. Okay, so what I'm actually going to do is I'm going to go back to our original picture and kind of remember the argument that we try to build. Okay, and the argument that we built was really based on this, right? Where we had the number of leaves plus the number of internal node is equal to the size of the tree, right? But what I actually argued was this, okay? This is what I started with because, I had this picture, okay? So what we did was we paired up each of the leaves with their parent, which was an internal node, all except for that one. That's where the minus 1 came from, right? So okay, so that's what we found, right? So the number of internal nodes was less than or equal to the number of leaves minus 1. Okay, it turns out that generalizes a lot better. Okay, so let me show you what I can do. Right, here's the case where I have some kind of a bigger, min order. Right, so the min order here, right, is 2. And now look what I can do. I can group 2 leaves with 1 parent. And then I'm left with 1. Okay, so maybe that's the correct generalization, right? Because what I have is that the number of internal nodes, right, can be less than or equal to, well, shoot, looks like I have the min order times NL of t, right, minus 1. Right? Actually, I take that back. The min order is 3. I wasn't counting those guys. So this should actually be m minus 1. Okay, that seems like a reasonable claim to make. Let's see if we can make it. Okay. Okay. So yes. Okay. That's what we'll try. So here's the picture, right? This is the similar picture to what we had in the case for a binary tree, except here the min order, okay? The min order, which we're calling lowercase m, is equal to 3, right? So I have 3 children right here, okay? Now I'm going to go ahead and group those as before, but I'll use a slightly different approach, okay? So what I'll do is I'll group these, right? And I have 1 internal node and 2 children, and here I have 1 internal node and 2 children, 1 internal node, 2 children, 1 internal node, 2 children, and then that guy's just living alone, right? So how can I generalize this kind of rule? Okay, And what you can see is that for each internal node, it's not just one leaf, but two leaves. Okay, so I can actually multiply this by 2. Twice the number of internal nodes should be less than or equal to the number of leaves. Okay, minus 1, right? Let's see if that holds. I have 1, 2, 3, 4 internal nodes, so this will be 2 times 4 is 8. And how many leaves? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, minus 1. So yeah, 8 is less than or equal to 9 minus 1. That's about as much as I can push it, right? Okay, so 2, where's the 2 coming from? I have 3 children, because that's the minimum order, and one of those will have children of his own, right? That's the pattern, and the other 2 are leaves. So this is actually equal to m minus 1. Okay, so that's what we think will generalize. Okay, so let's try to prove that. Okay, so here's kind of our picture, right? Like I said, we think that's a good generalization, and let's go, right? So m minus 1 times the number of internal nodes should be less than or equal to the number of leaves minus 1. Of course, we're going to use structural induction. We'll induce on the shape of the tree. Okay. Now we're going to use kind of an important fact that we haven't proved. Okay. So let's say that T is a tree that has height greater than 1. Okay. Then T has at least one internal node that has only leaves as children, right? So let's think about that. Okay, here is a tree, right? And the height is greater than 1. Okay, so that means that, well, it might look something like that, okay? Now, this guy, right, has children, right? And one of those is not a leaf. But I can just keep going down the tree and eventually I'll find all leaves. Okay? You know, if I don't, you know, in that step I don't find all leaves, then I just keep going down on one of the ones that's not a leaf. Keep going down until eventually I need to find that, right? You can actually prove that with structural induction, okay? It's not particularly hard. You can also prove it with mathematical induction if you simply use the height of the tree as your parameter, okay? So that's one possibility, okay? All right. So let's go ahead and take care of the base case, right? So in the base case, T is a leaf, okay? And again, I emphasize that that's because there are no empty trees, okay? So the number of internal nodes has to be equal to 0 because there's just the one node and it's a leaf, so there are no internal nodes, right? So what we get is the number of internal nodes, right, is equal to m minus 1 times 0, right? Which is actually equal to, this is actually equal to, by the way, this is just h, right? This is the number of internal nodes, right? Which is 0, and this is the number of leaves, okay? Which is 1, right? And in fact, 0 is less than or equal to 1 minus 1. Yes, the base case is taken care of. That's good. That should work easily, right? So let's try to do the inductive step, okay? T is not a leaf, and the theorem holds for smaller trees, right? In particular, it holds for the tree that results when you remove the children of one of the internal nodes that has only children leaves, okay? So let's consider what we're really doing. We have a tree, right, that looks like this, and let's say that this goes down, and eventually I have a node that has only leaves, okay? So what we're going to do is we're going to take that node, okay, and we're going to build a new tree that has the exact same shape of that one, okay? And it just stops at that node, right? Notice there are no children, okay? So what I've done is I've taken the original tree and a smaller tree, okay? This is not structural induction. Structural induction says that it's true for my children, right? I'm actually assuming that it's true for some smaller tree, right? This actually is an example of noetheric induction. It's a more powerful form of induction. We talked about that when we were doing the induction section. But here is an actual example where we need that, okay? So let's see what we have, okay? M minus 1 times the number of nodes of the new tree, right? I want that to be less than or equal to the number of leaves of the new tree minus 1, okay? I mean, that's what I'd like. So let's see if I can get there. What do I know about the number of internal nodes? Well, remember, I took a node, right, and I converted it to a leaf. So the number of internal nodes went down by 1, okay? What about the leaves? Well, I got rid of m prime leaves, right? All of these, right? They're gone. And then added 1, the internal node, right? So that's actually the number of leaves in the new system. Okay, so now it's just factoring, okay? So m minus 1 times the number of internal nodes, right? That's m minus 1 times 1, so that's how we get that. And then in here, we have a plus 1 and a minus 1. We'll get rid of that, okay? So that's how we get to this step, okay? And now what about the next step? Well, I'm going to have this parentheses and break it out, okay? So this is the same, except now I have minus m plus 1 instead of minus parentheses m minus 1, okay? And then, okay, I'm simply going to turn this around because, okay, what I can do is, what exactly is m prime, okay? Well, m prime is the number of leaves well, it's the number of leaves that I actually took out, right? I mean, I may have taken exactly the min order, but it could have been more. It could have been even worse, right? So what I can say is that m plus 1, okay, is actually, right, smaller than m prime plus 1, right? Or at least as large, right? So what I'll do here is I'll just take out an m plus 1 term, and I'm left with just 1, right? So basically m plus 1 can be, well, okay, m prime is less than or equal to that, right? So m prime minus 1 is less than or equal to m. Okay, so that's how I can make that argument happen. Okay, so amazingly, there it is, right? You know, it's proved in the inductive case. This is actually one of the harder inductive cases that we're likely to see. Okay, all right, let's see what we can do, right? I mean, we have a nice upper bound, so we have a lower bound. How about an even better lower bound, right? So this is what we did when we talk about full and balanced trees. Okay, so let's talk about those full and balanced trees. Again, we're going to define a balanced tree the same way as before, right? All the leaves are at level h or h minus 1 for some h, right? And as before, if you do find such an h, then the tree will also be balanced to the height of the tree, right? The height of the tree can fill the role of h. So if we just do that, we'll save a step, okay? So let T be a tree that is balanced to h with a certain number of leaves, right? The min order is m. And so here's what we're going to claim, okay? That m to the max of h minus 1, 0 is less than or equal to the number of leaves. Okay, that's a nice lower bound, okay? That's kind of an ugly term, but actually it's not quite as crazy as it looks. Suppose, for example, that h is 10, right? Then the max of 10 minus 1 and 0 is just 9. So I can forget about this, right? You know, that's just h minus 1, as long as h is a reasonable number, right? It's only when h is equal to 0, right, that I have a problem, because h minus 1 is actually minus 1, and then, oh, then it actually doesn't hold, okay? So it's just good to treat it this way and realize that we're only trying to special case the empty tree, or, you know, the leaf tree. Okay. All right. So we'll use structural induction. So if T is a leaf, right, then M is equal to 0, number of leaves is equal to 1, right, and H is either 0 or 1. So max of H minus 1 is 0, right? That's the beauty of using that max, right? So the theorem holds, and the theorem holds, again, I'm emphasizing that I'm using 0 to the 0. I'm defining that to be 1, okay? Now, otherwise, h is greater than 0, so this is just the same as h minus 1, right? I only needed that max for the base case, okay? So and the number of leaves in the tree is greater than or equal to the number of leaves in T1 plus T2 plus all the way out to Tm. Actually, that's even equality, right? Okay? So what we'll do is we'll use now our inductive hypothesis right here, okay? Because the height of each one of those trees is 1 less than what we had. So it's h minus 1 minus 1, okay? And I have m of those at least, right? At least m of those. So m times that, okay? Gives me that number, okay? By the way, there could have been m plus 1 tree, because this is the min order, right? So that's why it's greater than or equal to. I missed that, okay? All right, so final answer, m to the h minus 1. Perfect, okay? So that proves it, okay? Okay, so we now have the min order, right? We have a maximum, we have a pretty nice minimum, right? So let's combine those results, okay? And what we have, which is really quite beautiful, is that the number of leaves on a tree is between, you take the min order and raise it to the height minus 1, or you take the max order and raise it to the height, okay? That actually is just kind of the combination of the theorems we've proved, okay? So it's really a nice result. This is equivalent, right? So for binary, right, we had, I could have done 1 less than or equal to the number of leaves of the tree, 1 to the h minus 1, if you will, less than or equal to 2 to the h, right? And if it's full, okay, if it's full, then I can make that 2 to the h minus 1, right? And that's because there's the min order, okay? If the min order is, well, if it's full, then the min order is 2, right? Otherwise, the min order is just 1. So that works, okay? All right. Okay. Before I move on, I want to say something about trees in general, okay? So we've seen a lot of the bounds on the size of a tree, right? Now, why is this actually important? And one of the reasons that is important is that a lot of times trees are just overhead, okay? And the data, the important stuff, is in the leaves, right? This is the important stuff. And the internal nodes, right, are overhead, right? So what we want is to have the fewest number of internal nodes compared to the number of leaves, okay? And now we know how to do that, and that is to make the min order bigger and bigger and bigger, okay? So it all comes down basically to the height, h, right? We want this to be small, okay? And the way to get the height small is to have, well, for the same number of leaves, right, is to have a bigger fan out, okay? So that's our plan, okay? So we really want trees that are, quote, short and stout, right? Height is small, and in order to achieve that, they have to have a big fan out, okay? Now, this is the absolute ideal, right? The height is equal to log n, and I'm being vague, right, on the base of the log, okay? Mostly because, honestly, log 2, log 10, they're going to be reasonably be close compared to the number of nodes, okay? So just generic log, okay, to keep this between friends, so to speak. Okay. They don't actually have to be really balanced, okay? They just have to be close enough to balance, all right? So for instance, suppose that that I have a couple of places where it comes down with just the min order, right? And it's not quite as nice. It's not always the max order. It's okay as long as I'm not abusing that too much, okay? So for example, one of the things that you can guarantee, this is kind of a weak guarantee, the height is 1.5 times log n instead of log n, right? That's actually good enough. 1.5 times log n, like I said, it's pretty good, right? Take for example 1,000 leaves. Base 2, that is a height of 10, right? 15 compared to 1,000 is still pretty small, right? And if I take, for example, base 10, then the log of 1,000 is actually 3, right? So 1.5 would just make it 4.5 or 5, right? So yeah, this is excellent, right? As long as we have a nice log factor, 1.5 isn't going to hurt us, right? So the ideal is log, but small constant times log, I'll live with. Okay, so here is the big point, okay? I don't have enough mathematical machinery to be able to prove this to you, so you're just going to have to take my word for it, okay? And that is that the average tree is beautiful, okay? If you simply build a tree at random, it is very likely to be short and stout. And that's what we love in trees, okay? Now, why is that? You can just simply kind of appeal to intuition. So you think of your tree, and let's say that it's not beautiful, right? So it's got some leaves that are close to the top, and we really would like to distribute those leaves down, right? Well, when we add a new entry to the tree, it's very likely to go in one of those spots at the top, right? And so it's going to fill in the kind of the bare parts of the tree before it expands further down. That's a little loose. I mean, actually, that's very loose, right? But that's the right intuition, okay? That's actually why that happens, okay? Here's another way of seeing that same intuition. um, you have to get really unlucky to keep adding down the left branch. Okay? Every time that I try to add an entry to a tree, I always add it to the left branch. Let's say that I have a tree, it's got 10 nodes, but they're all coming down the left branch. Okay, so they look like this. Okay, and now I'm going to add one more. I have to get really unlucky to add it here instead of there or there or there or there or right. So chances that I keep making the tree bigger are, taller, are actually low, right? And the more out of balance it gets, those chances get even lower. So that's fantastic, right? Just by chance, trees make themselves short and stout. Beautiful.